Welcome everyone to the 5th doctoral student edition of the Geospatial Forum. My name is John Vogler. I'm happy to be here today. We have almost a full house. We have 4 great geospatial analytics Ph.D. students presenting today. Got a little housekeeping to do. One, we also have a UCOM photographer, Becky Kirkland, over there. She's going to be snapping pics throughout the event. And how this is going to work is each speaker is going to have 10 minutes, around 10 minutes to speak. And we're going to hold questions until all the presentations are over. If you do need clarification on something during a presentation, please do chime in, but otherwise hold your questions to the end of all the presentations. That ensures that everyone will be able to get through their presentation. What else? Also, Lois wanted me to remind everyone that all of the utensils, the plates, the cups, they're all compostable, okay? There's a bin in 5119. Okay, so we have today Christina Perella, Rebecca Composto, Owen Smith, and Randy Butler. Let's give them a round of applause, please. Thank you all for presenting today. We're going to start out with Christina Perella. She is co-advised by Dr. Adam Turando and Dr. Jelena Vukmanovic.
Thank you, John. Hi, everyone. My name is Christina Perella. I'm a 3rd year in the PhD program. And as mentioned, I'm co-advised by Dr. Jelena Vukmanovic in the Land Change Lab and Dr. Adam Turando, who's a CGA faculty fellow who's affiliated with Applied Ecology. So today I will be talking about the 2nd chapter of my dissertation, Climate as Push and Pull Forecasting Movement of US Populations, and also how it kind of ties into the broader research project that I'm part of as my dissertation. So this broader project is titled The Long View, Development of a 500-Year Climate Adaptation Planning Framework with the Eastern Band of Cherokee Indians. So the goal of this project is to co-produce a climate adaptation plan that focuses on these multi-generational time horizons to align with tribal values of multi-generational land stewardship. And so through these modeling efforts and eliciting tribal values through participatory workshops, we hope to support both shorter-term decision-making and long-term tribal resilience through scenarios of future landscapes like forest change, growth demands related to population and development, and then sustained access to natural and cultural resources under future land use and climate change. I wanted to give a little bit of background about EBCI for those who are not familiar. This is a federally recognized sovereign nation located in the Qualla Boundary, which is about 57,000 acres of forested lands in the southern Appalachian Mountains, which is shown in this red area here in western North Carolina. And there are currently about 16,000 enrolled members in the tribe. But historically, the pre-colonial homelands of the Cherokee was spread over much of the Southeast. Unfortunately, as with many tribes in the eastern United States, their land was taken through cessions, treaties, and kind of legal and forceful pressure to move further west. So as you can see from this map, the homelands have shifted significantly over time. And I also mentioned that co-production is a major goal of this project. So because EBCI is a sovereign nation, they have their own governance and agencies. So we've been working with the EBCI supervisory biologist, Caleb Hickman, who works in their natural resources department. He's been instrumental in co-developing this project with us from the beginning. And we've also worked with the tribe's cultural IRB on creating a data sharing agreement. And we have some planned community engagement through workshops and other outreach opportunities. So broadly, my 3 dissertation chapters combine models of climate change, landscape change, and human population change to understand where natural and cultural resources might be vulnerable in the future. But as I mentioned today, I'll be talking about my 2nd chapter, which really focuses on human migration under future climate scenarios and how that can impact land use change in the region. So the literature suggests that human migration will become an increasingly important adaptation to climate change as people migrate to safer and more comfortable destinations. There's a widely cited econometric model by Jordan Rappaport, which found that quality of life and milder weather, specifically like milder winters and summers, have become increasingly important pull factors attracting people to a place over the last century. So we wanted to extend this model to kind of quantify that relationship between climate and human population change in the United States. And so a little bit more about this model. It's called Moving to Nice Weather, and it uses a regression model to quantify this relationship between 5 climate variables and annual population growth rates at the county level for the contiguous US between 1970 and 2000. So the climate variables include winter weather like January maximum temperature, summer weather represented by July relative humidity and July heat index, and then precipitation variables, including the amount of precipitation and also the average number of days on which there was precipitation. And then there are also a set of control variables in the regression model, including 7 geographic variables related to topography and coastal proximity, and then 14 population variables that account for things like the initial population density of counties and things like market potential. So this is kind of the spatial representation of this regression model. So this is the expected population growth at the county level based on the results of that regression model. And I also wanted to point out, I mentioned that the original model only goes through 2000, so we wanted to extend this using climate data through 2020. So the darker blue areas represent a negative growth rate or a declining rate. And then as you get into the green and yellow, it's a moderate growth rate, and then the orange and red represent a higher growth rate. So the spatial results are kind of expected. You can see that warmer areas like Florida, Arizona, and coastal California show those higher growth rates. And in comparing this to Rappaport's results through 2000, it is a similar spatial pattern. And then some other interesting results. So these are just graphs of the resulting coefficients of those climate variables in that regression model. So the left two show the original time period of 1970 to 2000, and then the extended 50-year period through 2020. But then I also ran the regression for each decade between 1980 and 2020. And as you can see, 1980 to 1990 and 1990 to 2000 are pretty similar to those longer averaged time periods. But as we get to more recent decades, that relationship really weakens. So basically, like the contribution of climate to population change is weakening over more recent decades. And so this is for January maximum temperature and July heat index, which are kind of the most important variables in this regression model. And when I talk about moving to nice weather, I just want to point out for January, it has that kind of strong positive relationship. So as January temperature increases, we expect population growth to increase as well. Whereas for things like July heat and humidity, it has a fairly strong negative coefficient. So we expect that as the temperature gets hotter in the summer, we expect the population growth to decrease. So we're wondering why there's this, kind of strong weakening relationship. And it's been shown in recent literature and media that people are still moving to areas that have high risk of climate disasters. So that includes areas like the coast that are vulnerable to sea level rise, but especially these kind of Sunbelt states towards the bottom of the country. People are moving to places like Arizona, where the July average high is like 108 degrees. So people are still moving to places where we might not consider it good weather, especially as it gets hotter and hotter. I also want to point out, moving is just easier nowadays. I think people's lifestyles make it so that we're able to move, and we can still stay in touch with people through things like social media. And also remote work makes it easier for us to live away from urban economic centers. So still kind of tinkering with making sure that our model is a good recreation of this original model. But the goal of this is to use this regression model to actually project future population growth using future climate projections. So we're going to be using two climate scenarios, RCP 4.5 and 8.5. And then I plan to compare that to published results from Hauer, which also projects population growth in the US at the county level through 2100, but instead using the shared socioeconomic pathways, which is kind of a more updated set of climate scenarios that include a set of socioeconomic variables instead of just greenhouse gas emissions. And so you might be wondering, like, why are we talking about the county level population growth? What does this have to do with the tribe and the study area? So the reason that we're doing this is because we're interested in using our results as kind of a population modifier to run a climate-informed migration scenario using the Futures Urban Growth Model. So a lot of people in this room are probably familiar with this model, but it uses a set of environmental, infrastructural, and socioeconomic predictors along with historical development patterns and historical population and future population projections to predict development outcomes spatially. So we'd like to run two different population growth scenarios. One will be like a business as usual scenario using currently available county level demographic projections. And then our second scenario will use this kind of potential for increased population in these areas due to climate-driven migration. And so the reason we're interested in development in this region is because land use has changed a lot in Western North Carolina. So since the 1970s, there's been a pretty drastic increase in population and development. This is primarily attributed to amenity migration. So this is when people move basically to seek a greater quality of life. That could be through larger properties, more space, more privacy, and especially access to nature and outdoor recreation. So in this region, that's driven by this large network of protected areas. We have Great Smoky Mountains National Park and some national forests in this region. But then there's this potential for an influx of climate-driven migration as people might start to move away from those areas that are more susceptible to climate risks towards the mountains, which are expected to have lesser climate impacts. And so we want to account for this potential increased growth in this region because changing land use and growing population can have impacts both on natural resources and socioeconomically due to concerns like gentrification and kind of a perceived changing of the way of life for the populations that already live there. And so our future work that we're interested in is potentially using the Futures results as an input into the Land is to Forest Landscape Change model to kind of represent land use change in this region and how that might impact natural and cultural resources and where they might be vulnerable in the future. Sorry, my mouth is so dry. So that's all for me. I just want to say thank you again to my advisors and my lab, as well as the Southeast Climate Adaptation Science Center for supporting this work.
Okay, up next, sorry. Up next, we have Rebecca Composto, and she is advised by Dr. Perella Tolber.
Yes, so thanks, John. Hello, everyone. I'm Rebecca Composto, and I'm a third-year PhD student in the center and in Dr. Tolber's lab, as John mentioned. And before I get started, I want to thank my lab mates and advisor for their input and feedback, and also the center, as well as NC Space Grant and the US Geospatial Intelligence Foundation for funding that made all this work possible. So today I'll be talking about using satellite imagery to map urban flooding. This photo here is an example of some urban flooding It is flooding in Philadelphia that happened after Hurricane Ida. So one reason we might, or one reason we spend time mapping floods, and some reasons why they might be useful and important, is ideally they can help residents as well as city planners and emergency managers to make plans for the future, and as well as recover from past events. And this photo here might look like a river, but it is actually Interstate 676, which runs through the city of Philadelphia. And after Hurricane Ida, it did flood. And so mapping this out and knowing where this occurred could help people make alternative transportation plans and also place mitigation efforts to reduce this flooding into the future. So yeah, I'll be talking about using satellite imagery to map these types of floods, and then some things we can do with those flood maps. A little bit of background about Hurricane Ida. It was a Category 4 hurricane that landed in Louisiana, came up to the northeast, stalled, slowed down, and released a ton of rainfall, caused 75, I've seen 80 billion in damages, or 80 billion in estimates as well. And in Pennsylvania, it caused 2.5 to about 3.5 billion in damages as well. And when I started looking into this in 2022, I couldn't find a flood map of this event. And so I really wanted to dig into it some more and see if I could make a flood map of this event. So starting with Pennsylvania, I selected Philadelphia and then some surrounding slightly less urban counties. I was interested in an urban area because it's more difficult to map floods in urban areas than, say, a farmland or bare soil. Urban areas have more complex topography, taller buildings with more shadow, so it's just a bit more complicated. And there just so happened to be cloud-free Sentinel-2 10-meter satellite imagery. Pretty rare to get cloud-free imagery, especially optical imagery after a flood event, so this was pretty lucky. So once I had the imagery, it was a matter of what methods to use. And machine learning has been shown to be more accurate than using a single index. At least that's what the literature shows, is it's more accurate. And I also explored some deep learning. However, for urban areas, floods come in quickly and they also leave quickly. So they're not often captured by satellite imagery, which means there's not a ton of training data, and deep learning models require a lot of training data. So random forest doesn't require a lot of training data, and it is robust to some mislabeled data. For the training data, I did hand draw the training data, which wasn't too tedious. And I also used some PlanetScope imagery, so separate and higher resolution imagery. That was 3 meters to make that training data. And now I'll talk about some of the inputs to the training data. If you do land classification, ideally this is some useful information. If you don't, hopefully it's still a little interesting. So first off, I included some fractional coefficients. So the percent of these 3 categories: urban, water, and vegetation, the percent of each of those within each pixel. This was a recommendation from Dr. Varun, who just graduated. And yeah, that really boosted the accuracy of the water and flood class once I added those in. So another pro of random forest is you can see the relative importance of the different inputs. And one thing I found was that the modified normalized difference water index was the most important water index of all the water indices that I included. And then slope was also pretty important. And then I also included, and it sort of spread throughout the band importance or input importance, I included a focal mean or a 3x3 window. Random forest doesn't take into account any spatial information. Deep learning or some neural networks have that spatial component. So this 3x3 window is a way to incorporate spatial information into the model. We'll see if this runs. Oh yeah, so basically after I had all of that, I classified the imagery and the different inputs into flood and flood extent. And the light blue areas are floods. And this area here is that Interstate 676 that I showed earlier. And the bright blue pixels show that I was able to capture the model, and the inputs were able to capture that flooding. Some things you might also notice is there are some gaps in the different polygons of flooding. So optical imagery can't see through bridges. So that's one limitation and something you have to keep in mind when using these types of maps. The accuracy for the model was overall high. And more importantly, for the flood class and the water class, it was also relatively high. Some caveats to that are, again, optical imagery can't see through bridges. And also for some of the smaller streams, they weren't picked up by the 10-meter imagery. So once I had the flood output, I also wanted to see how that compared to a probability map, specifically FEMA's probability map. And it's not a perfect comparison comparing one flood extent to a probability map. They serve different purposes. But since there's this misconception that if you live in the minimal hazard zone, you have no flood risk, I really wanted to visualize and also quantify that there is still risk if you live outside of this zone. And it'll pop up. Yeah, so this bright blue area, I don't have the permanent water overlaid here, but you can see certainly some flooding does occur outside of that 100-year, 1% annual chance FEMA flood zone. Another thing I looked into was if vulnerable populations were disproportionately impacted. So at the global scale and the national scale, vulnerable populations tend to be more impacted by flooding, at least flood probability and flood risk. And what I found, well, I guess I scooch back a bit. I use Lorenz curves, which are popular in income inequality studies, and that folks at UC Irvine have sort of adapted to study flood impact. But for my couple of counties for one event, I found opposite to this global national trend that vulnerable populations, as defined with CDC's vulnerability index, were not disproportionately impacted. But the big caveat there is it was one event for a couple of counties, even a couple of counties within the whole Hurricane Ida event. So all the methods are available in a paper, and the flood extent is available in Zenodo, ideally useful and available to folks making decisions related to flood mitigation and other planning. And the main takeaway here is that satellite imagery and the model I created can be used to map urban flooding. And going into the future, I am working, and currently I'm working on calculating flood depth, because depth is more of an indicator of damages. And I'm also looking into damages, depth. And I'm using PlanetScope 3-meter imagery. So getting a little bit higher resolution imagery as well. So yeah, thank you.
All right, up next we have Owen Smith, and Owen is advised by Dr. Josh Gray.
Hi, so I am a fourth-year PhD student here in Josh Gray's SEAL lab, and I am presenting today on my work pertaining to accelerating land surface phenology estimation with a computationally efficient BLSP. And this will be the only map in my presentation. It's kind of what I'm going to talk about is less on answering science questions with maps, but how we're actually even able to produce the data to get to that point in the first place. So first of all, what is land surface phenology? Land surface phenology and land surface phenology metrics are the seasonal patterns of vegetation activity observed from satellite data. It's not always observed from satellite data, but in our case, that's what we care about. It can be observed literally just from you standing outside marking when these seasonal patterns occur. But remote sensing allows us to do it at continental and global scales. It provides crucial data for climate change research, ecosystem monitoring, agricultural management, anything you can think of that might involve a plant. And that leads us to the Bayesian land surface phenology, or BLSP model, which is a model that was developed by my former lab mate, Jay, published in Remote Sensing of Environment a couple of years ago. It's a hierarchical Bayesian model for extracting these phenological parameters from remote sensing data. It provides posterior distributions via an MCMC sampling algorithm, and it enables statistically robust trend analysis across decades. What it's really great at is it's able to ingest a bunch of sparse, potentially noisy data across essentially the entire Landsat archive and produce these photometrics going back 30, 50 years at a resolution we were previously unable to do that at 30 meters. What it does is it samples essentially all of these parameters here. So the 7-parameter double logistic model, this vegetation index here, that is roughly what a phenological curve for a given year will look like, pertaining to things like start of season, end of season, senescence, the like. And what an MCMC algorithm does is it essentially samples from this higher distribution, and hopefully we converge on a representative understanding of the probability of that distribution. It's a great model. It's lovely. It allows us to do things that we weren't unable to do previously. However, in the original paper, it took 13,000 compute hours for a single Landsat scene on NCSU's HPC. For reference, a single Landsat scene, while it's quite a few pixels, it's only 650 by 653 pixels. Granted, that's for 36 years, but that's a huge computational bottleneck if we want to move beyond a single tile and start answering questions at even the state scale. The rest of this presentation will focus on, well, how do we solve that? So our approach uses a blocked sampling of the parameter vector approach, and I'm going to focus less on the more statistical algorithmic part of things, but another part of that is it uses a metropolis within Gibbs algorithm for more efficient exploration of the parameter space so that we can converge on the real values better. The algorithm is written in C, which allows for an immense amount of control over certain optimizations that I'll talk about. We're able to provide streaming quantiles of samples, which gives us constant time and space complexity. And then it results in approximately, on average, a 90% increase in speed per pixel just on a single core. So first part of that, memory optimization. So I essentially set it up so that I'm able to compute exactly how many bytes are needed for the model, and I'm able to allocate that immediately at runtime. So we're not having to worry about with each iteration growing our memory space. And yeah, that's an expensive thing to do, to have a computer search out for memory. So it also prevents fragmentation, stuff like that. And then for optimizations later, it allows us to have really nice cache alignment, so that with each CPU cycle, we're not wasting CPU cycles trying to fetch the data we need to actually do the computations. And so just as an example visually of what that looks like, for our continuous allocation, we essentially we have this block of memory. We can iterate, we can bump the pointer forward and then free it all at the end. Traditional allocation, every time we allocate, say, an R, a vector, it goes out, it searches your computer for space where you can fit that, and then it allocates that memory. When we grow that vector, it does that again. And it does it again and again and again, growing it by about two times. And then once it starts deallocating things, we end up with our memory address space looking really wonky, and kind of it makes it so we have to spend more time looking for space to allocate. And if we're running an MCMC algorithm, which is tens of thousands of samples and iterations, it can get not fun very quickly. So the cache alignment with all of that is really important, because we're also leveraging single instruction, multiple data instructions, which essentially, instead of parallelizing just by splitting it up on a bunch of CPU cores, well, modern CPUs can do that just on one core by processing multiple bytes with a single instruction. So just really quick example, instead of having each cycle multiplying things by 2, we're able to pack in 16 or 4 16-bit integers into one kind of cache line, and just with a single instruction, multiply that. And so we've now reduced that by a factor of a couple. So depending on your architecture, you can do, and also your data size, you can do 2, 4, or 8 values at a single instruction. So it looks a lot like this. It's really gross. I'm sorry. But you basically, you have to, it's also fun because you have to go through all your kind of original code, sometimes look at the compile assembly, and you figure out how you can actually express that in these sort of instruction sets. So this is what it looks like for my ARM Mac machine. For kind of your PCs will look different. And then basically that single double logistic green down function, we're processing 264 floats at a time, and we can iterate over that. And so now our iteration is reduced by 2. My mouth is also dry. So we're also, with all of these, we have to take all these samples, right? So at a minimum 10,000 samples. And so we have to store that somewhere. And so in the original implementation, all 10,000 of those samples are stored in memory until the very end, and we compute the quantiles on that, which involves then sorting all the samples and then finding based off that where our quantiles fall within. And that can take up a lot of space. So for instance, for our data set, 36 years, 10,000 iterations, 7 parameters at 8 bytes, about 20 megabytes per pixel, not a lot. 8.57 terabytes for full Landsat scene. We're now in the realm of a lot. So I am using the p-squared algorithm, which is piecewise polynomial algorithm that computes the quantiles in an online fashion, meaning for each quantile we want to compute, we only store 5 values ever for that. So it's constant in that. And so now we're down to 30 kilobytes per pixel and 12.8 gigabytes for the full Landsat scene. And all of that's without sort of, for storing it on disk, the compression that comes into that. But when it comes to compression, to be able to use it, you always have to decompress it. So just something to keep in mind too. So overall improvements, original BLSP, really, really long, 13,000 compute hours, pretty limited for large scale applications. We're now about 90% faster at a pixel level. So roughly in the range of milliseconds for a pixel now. We're able to get an additional 25 to 31% improvement by targeting single instruction multiple data for various CPU architectures. We have minimal memory footprint, and it's now largely feasible to scale it to larger regions. Why this matters? Ask myself every day. So we've reduced from potentially months to days. Again, we can answer questions about more things. Preserve statistical rigor and uncertainty quantification of the original algorithm. We're able to do more frequent phonology monitoring. Technical takeaways: low-level optimizations have major impact on high-level models. Memory layout is critical for modern CPU architectures. Algorithmic improvements plus data-oriented design can lead to the best results. And scientific models need computational efficiency for real-world use. And that's it.
Okay, our fourth and final speaker today is Randy Butler, and Randy is advised by Dr. Natalie Nelson.
All right, hi everybody. Of course, my name is Randy Butler. I am a fourth-year PhD candidate here at in our geospatial analytics lab. We know where we are. Sorry. So this is my research on, which is actually now my first chapter that does not have this title anymore. However, because this is a presentation I've done already stuff, we're leaving the title as is. My research is called Assessing Climate and Weather-Driven Impacts of Crops to Crops of the U.S. National Crop Yields and Losses, which data source is best? And so I want to just start out by saying, like, in the realm of agriculture, the USDA NAS, or National Agricultural Statistics Survey, is the premier resource or data resource for evaluating agricultural productivity, and including climate-driven losses. But unfortunately, participation has declined. And what I mean by participation is NAS data is basically given or created by user input or voluntary surveys and census data. So over the course of time, as you can see in this plot here, it has increased, like significantly dropped off. Like back in early 2000s, it just sharp decline. So because of that, it's causing some issues with reliability. And this is very important in the realm of agriculture because with extreme weather events that can affect our crop production or our food supply, we need to find another resource to at least be able to help these farmers understand what's going on with their products. So what my research is doing is trying to look at alternative resources that can actually provide more information and fill those gaps in the data that is not just being accommodated by NAS. So with my research, we found an alternative resource. There are a lot more, but the best one that we found is utilizing risk management agencies' data. So we did a quick comparison to understand the difference between these two, and the three main factors are they're different on their intent, the method that they're collecting data, and the location that this data comes from. So with NAS, or like I said, National Agricultural Statistics Service, they collect agricultural production information, again, by the means of producer input on a voluntary basis. They collect this from, the method is collecting data from voluntary self-reported data, like I said, and the location of this data is typically collected mostly from states and sometimes counties. Whereas for RMA data, they collect information on crops, causes of loss, and insurance rates. And this is also mandatory because when you get insurance, you need to provide that data. If you want the funds back, it's mandatory to give that information. Another significant difference is in the location. Crop data is collected from counties and states, not just states, but at all times counties and states. And that is a big significant difference when I was looking at this data. So to do this research, to plan a study, our objectives were basically quantify differences in NAS and RMA data across the US for 4 major commodities. And these 4 major commodities are corn, cotton, wheat, and soybean. The reason we picked these is because corn, cotton, wheat, and soybean accounts for 90% of the harvested crops in all of the United States. And we wanted to also capture interannual variation over a decade. So the study went from 2011 to 2021, so it's technically 11 years. And then we also wanted to characterize the differences between NAS and RMA data to summarize the advantages and disadvantages of each data set. So the methods used in this were, of course, collecting the data, cleaning the data, and now that has a mop and a broom or a bucket. I promise you, I probably cleaned like a whole warehouse, just the amount of stuff I had to do with this. And then also perform a comparative analysis using summary statistics and correlation. So the first thing we did was, when I said something about location, how counties and states vary, we wanted to see where it was represented or what locations were actually represented in both data sets and if there was some overlap. So we checked for all the 4 crop types, and we found that for corn, corn grain and soybean, they're the only two crops that have county data in NAS and RMA, whereas cotton and wheat only could give us state data in NAS. So to do a one-to-one comparison, we had to only use state data from RMA. So we found that in the majority of cases, locations overlap. Both report the same places. However, when you're looking at one resource over the other, RMA outweighs the amount of locations that they report. So they typically report significantly higher locations than that of NAS. So that was important. So we're like, okay, cool. Let's try to figure out now what the crop loss is, like the actual amount of acres lost for these data sets are. So we did a crop loss calculation, and this is also when the data cleaning comes into effect, because NAS does not produce crop loss data. It tells you planted and harvested, but does not tell you the acres of crops lost per location. It will tell you what crops are lost, but it won't tell you where. So we basically did planted minus harvested and got total lost acres as a representation. And then we used the reported values from RMA for crop loss. And those are typically created by using insurance, and they calculate them based off of acreage and insurance-based losses. So for corn grain, and actually all of them, because we're still doing the top is counties and the bottom is states, RMA outperforming on all of them. They're showing more crop losses than NAS. And we also think there's a reason for that in some capacity, because there's another caveat. NAS has this feature for their counties called, or this variable called other counties or other reported counties. So this means that in this particular state, we don't know what counties these represent. We just get a number of, hey, these counties their names are excluded, but there might be like 500 crops lost. And you can't compare that directly one-to-one with the location. So we wanted to try to figure out if maybe in these instances, whereas before, the unmatched counties, like the counties that were only reported in RMA, maybe those numbers might match up to these other counties or other combined counties. And no, they don't. Sometimes, in the very few cases where we could do counties like here in 2016, NAS outweighs RMA, but that's not always the case. So our next step was to try to see if we could see the difference spatially. So we wanted to see if, like how we said, location is not necessarily one-to-one. We just wanted to see like, well, maybe there's a certain region that's just reporting data more than others. So what we did was we calculated acreage loss difference. And essentially that was basically kind of doing a positive and negative type thing. So RMA, you get the average of their losses, and you get the average of NAS losses and subtract from one another. So RMA will be a positive number if it's in favor of that, and NAS will have a negative number if it's in favor of that, basically showing areas that have either more loss reported or other. So for corn grain, soybean, cotton, and wheat, we all still keep seeing RMA as kind of the higher reporting agency or the reporting data set. And you can see some relationship to location where like corn grain is kind of the Midwest area, and then soybean follows the Mississippi River. But because cotton and wheat are just states, you can infer that there's some type of location relation, but it's not necessarily going to always be that way. I don't want to make assumptions. So that kind of basically gave us an understanding of how losses are looked at. So then we were like, okay, well, let's check out yield, because farmers need to know their yields, and that most definitely helps them with productivity and their reporting. So we decided to look at all of these crops from the year 2020 to in 2021. And as I mentioned before, the study is from 2011 to 2021. So the reason why we chose 2020 and 2021 is because RMA at one point for yield utilized NAS data to calculate their yield. In 2020, they decided, we're not doing that anymore. It's taking too long. We're just going to do it ourselves. So that made the numbers change. So we wanted to see if RMA had they're compared to NAS was either closely correlated or just extremely different since they're using different methods. So we found correlation between all of them, all crops, for all years, except the crops that had the highest correlation, of course, were cotton and wheat, whereas the lowest correlation values came from corn grain. Now, we believe that cotton and wheat had the higher correlation values because it has such a small reported group, because it's just the states. So you have 50 states total, and you're not even using a full 50 states for this. So you're probably going to get a higher correlation. Whereas corn grain and soybean, as you can see, is a more dense plot for yield. So they had lower correlation coefficients. However, they are still correlated. So we wanted to, again, see this on a spatial view to see if there was anything significant. And we did the same kind of thing that we did before with the crop loss, whereas the higher the number is, like the more positive the number is, it's going to represent RMA or in favor of RMA, versus the lower the number, the more negative or orange is going to represent in favor of NAS. So we just basically took the average yields and subtracted them from one another to see if the difference was more significant in the RMA side or more significant in NAS. And we didn't really see, I mean, you could see that it's more favorable from RMA, but it wasn't that big of a significance because these are sometimes small numbers like 0 to 110, and this is more closer to 0 than something extreme. So it just depends. So we were kind of looking at that to see if it made a difference, and it wasn't that big of an issue. So with all of the research that we did, the main takeaways that we got for this and what this means in so many words is, as y'all saw, RMA has more spatial data coverage and reports greater losses for corn and soybean, as well as the other crops as well. RMA also includes loss, whereas NAS does not. So in RMA data, it will tell you, hey, this was a loss caused by drought. This was a loss caused by excessive moisture. This was a loss caused by I don't have money. Things of that nature. Whereas NAS, nothing. It will say sometimes loss caused by organic crop using pesticides, something like that, but it's not really specific or detailed enough to really get anything out of it. However, as great as we did, this does not represent the 10% of other crops that we have. So like I said, corn, cotton, wheat, and soybean, there's tons more crops in this world, and this data does not do a good job at representing that. So there needs to be some other type of comparative analysis for specialty crops and things or crops in specific locations. And that is when NAS and RMA will show the true comparison, because RMA does not always show specialty crops. And sometimes NAS does not either. So if more research can be done, you can kind of figure out which ones are best. So again, further research on specialty crops and crops in specific locations versus the entirety of the US should be performed. With that being said, it's very much based on what you're looking for and who your audience is and what you're trying to figure out. So that's what we basically understood. And this basic data, or this comparative analysis, basically is supporting me moving into my second and third chapters. And it basically supports why RMA data is actually advantageous when you're trying to compare losses and understand why climate change and extreme weather affects things. Yes, and as I said, is heavily influenced by crop type and data, crop type and location. So with that being said, that is the end of my presentation. I want to say, is there questions? I know we're holding questions to the end, so I guess whenever you want questions for everybody, this represents all of us. We can go further. Thank you.
Yes, so we do have time for questions. I'm happy to pull up any presentation if you have a specific slide you want to reference. And let's all work together to pass this mic around for the benefit of those online. So you would have to be at the back of the room.
Randy, thanks for your presentation. I'm familiar with NAS because I use it a little bit, but RMA is new to me. Is that a federal or is that a private?
It's also under the USDA. Just you know how USDA has like 5 million.
Yeah.
It's one of those 5 million.
Do you know? Do they use some RMA? Do they use some kind of cutoff to figure out like a quantity that they'll report on or something like that?
They're all their data is based. So whoever signed up for insurance from their state, whatever time frame they have to report that insurance, that's when it is. And I think it might vary slightly state to state, county to county. I'm not 100% sure, but it's just like I don't know if you're familiar with like the NRCS or the farm.
Yeah.
Like you want to get paid for this tornado that hit your property, you need to tell us by this date.
Sure. Okay. Yeah. So they probably don't deal with like little mom and pop operations. They probably deal with larger industrial kind of thing. Oh, they do.
Large production, small production, or whatever.
Okay. Cool. Great. Thanks.
I have a question for Randy also. Is there any validation data you've come across to determine like which data set might be more accurate?
Yes and no. So this study is complex in some aspect because there's some, like I said, I cleaned a whole warehouse of data at this point. So there's papers that say that NAS is wonderful. However, they're doing a one-to-one comparison and you'll be like, oh, so NAS has 40 counties. And you're literally only comparing that to RMA of the 40 counties. And that's not a fair validation to me. You're not considering the whole data set at all. Whereas there's some others that are favor of NAS. I mean, not NAS, RMA, but seems to be kind of like a area of contention for all sides because people like what they like. And one is a little more accessible. NAS is extremely accessible. Like I said, it's like the bee's knees to most people. So you're going to see more data supporting that, but I don't really have like a solid validation paper that kind of tells me one is better than the other. I had to basically do this and other people are like, oh, this works. This is great news. Maybe it can help us. And maybe it can. I hope so.
Yeah, thank you.
You're welcome.
I think you had mentioned that like our may outperform NAS because it has recorded higher loss. Does having a higher loss indicate an higher accuracy?
I didn't hear does having a higher loss.
So you said our may has recorded like outperform NAS majorly because it has like record of higher crop loss. So are you using the number of laws as a yardstick for accuracy? That's my.
It's the last part as a yes. Oh,
Yeah.
I'm not. How do I explain this? I'm using it as a factor of accuracy, but I'm more so using it as a factor of I have a lot of data that I can use from it. If I have gaps in one resource, I would rather have one that has more data for me to actually utilize and understand what's going on. And that doesn't mean that RMA data is accurate at all. And I did say outperform. I maybe should use another word. They just out data, let's say that. But it doesn't mean that the data is necessarily accurate because I am also not in the fields ground truthing this, but it does mean that it does have a substantial amount of data that I would rather have more samples than barely any at all, if that makes sense.
I also have some questions for Randy.
Okay.
Sorry, your comparison is just too interesting, so it kind of engaged me on estimating crop yield from remote sensing satellite data.
Mhm.
So I was wondering if there's a way to compare it or validate our collected data set from the space. If there's any study done on it. And then my second question would be, I wonder if there would be a way to aggregate spatially from counties to states, and that would enable comparison across the two data sets. So we don't have to do one by one, county by county comparison, and we could aggregate, for example, from monthly to yearly data. And would that be another insight?
Okay. So let me mentally go back to the first question. If we can use essentially remote sensing to calculate yield is kind of basically what you're asking.
Yeah.
So how do I answer this? That's a thing that I've been trying to figure out. And it comes, of course, as you know, with satellite data, you have to make sure that the data set or the imagery you get is within the season. But when it comes to understanding yield, you always have to know kind of what's harvested to understand the yield. And that takes somebody giving you that data set, like that actual number. So what makes this a little hard is the imagery, having that available, because a lot of these crops are in a season that has rain. My next chapter actually focuses on winter wheat because that's a year-long crop more so than other ones that are in the summer, and you get a lot of clouds. You can't read through clouds all the time, and I'm not gonna do any cloud scrubbing. I'm not. So yes, in some, I feel like there's a potential to do that, and I feel like the best way to do that would be with the use of drone data, because you're directly over a plot and you can kind of see what's going on. I think there's research in Nebraska that do that with the corn. They have the Super Bowl camera, the one that goes through the stadium, and they literally do that with corn just to understand what their yield will be. So it's possible. It just has to be on a high, fine scale resolution type of situation. Second question was aggregation. So actually I did aggregate when it came to the states for wheat and cotton, because RMA does have county data and state data, but it doesn't have state individualized like that. Whereas NASA just, oh, Alabama, they're like 500 crops. So I had to basically average that out, or sometimes total it out, depending on which one I was doing. If I was doing yield, it was more of an average. If I was doing crop loss, it was totaling it out to see how much of this crop was lost within that state. So that's the way I have to aggregate it, because the USDA does not talk between sub-agencies very well. That's something they would have to do, because they also have very dirty data, even if they were to do it. And there's a problem of even cities, like, for example, Baltimore. In NAS, it might be Baltimore, or actually in RMA is Baltimore. In NAS is Baltimore County, Baltimore City, 3 different types of money, like numbers. So you have to clean all that up. So it's not so much a question of can you aggregate it, it's can you have a uniform system to input this data so it could then be translated over to have a comparison between states over time.
Can I still ask some questions? Do we have time?
Oh
Okay.
God.
Well, maybe this will be rapid fire, but I have a question for Owen. So the process you developed, is that transferable to, I guess, like other types of analyses that aren't the like Bayesian learning, MCMC phenology assessment, or is that specifically tied to that type of assessment with that type of data? What's the transferability?
Yeah, it's most of the work is on specifically for that model, optimizing that. The techniques can be used for any sort of computational process or any sort of research software you need to write, though.
Cool. And I'm going to quickly ask one more for Christina. So you're using like a lot of, I guess, like, I don't know, quantitative assessment models to assess parameters that are of like cultural importance to a group of people. How do you translate cultural values into like such a quantitative process?
Yeah, that's a great question. And that's where that participatory engagement comes in. So we're interested in like finding out from the tribe, like what resources are important and why. So for example, not really related to the population modeling, but in my third chapter where I'm going to be doing the forest change, Landis is parameterized for, species in the Southern Alps, but the tribe might not be interested in specific species, but more like functional groups or habitat types or like habitat suitability for wildlife or gathering sites or things like that. So we haven't gotten to the point of doing those workshops yet, but we're hoping to kind of use that feedback to like map priorities to those specific resources that we're modeling. Does that answer your
Thanks. And for Rebecca, go birds.
Go bird.
Thank you all for coming, and let's give our student presenters another big round of applause. We'll have refreshments back there. Thank you.